Hello and welcome to this 10th lecture on algorithm selection and development in this course Master in Artificial Intelligence. So in this lecture we will talk about how to do hyperparameter tuning, basically to help you select and develop appropriate algorithms that can help you become successful artificial intelligence engineer. So let us start by knowing what is hyperparameter tuning. So hyperparameter tuning, also known as the hyperparameter optimization, is a process of finding optimal values of those hyperparameters, to maximize the model performance. So it's figuring out those hyperparameters that we talked about and how to find those values that are best for to maximize model performance. Now, what does it involve? It involves systematically searching through a predefined hyperparameter space. So there's a predefined space within which you need to find the right value systematically and evaluating the model's performance for each combination of hyperparameters. So it's a quite a painstaking task. And the techniques, what are the techniques for hyperparameter tuning? Now, the techniques for hyperparameter tuning include grid search, random search, and more advanced methods like Bayesian optimization and a genetic algorithm. And we will take a look at these as we go forward in this lecture. Now, the performance of each model variant. So you will have multiple variants of the model as you have different levels of hyperparameters, is typically evaluated using cross-validation to, as we talked about the cross-validation earlier, to ensure robustness and generalization. So this is how you evaluate the model performance. And what does it help? Hyperparameter tuning helps in fine-tuning the model and improve the performance on the new data that will come up, the unseen data, right? Okay, so that's what is hyperparameter tuning. So the question is, what are the core techniques for hyperparameter tuning? Now, these includes, as we were talking about, grid search and random search, and more advanced methods like Bayesian optimization and genetic algorithm. So these are the four core set of hyperparameter tuning techniques. Now, let's look at what is grid search. So grid search is a technique, hyperparameter tuning technique used to systematically search for optimal combination of hyperparameter values for machine learning models. And it works exhaustively. It works by exhaustively evaluating a specified set of hyperparameter combinations and selecting the combination that give the best performance according to a predefined evaluation criteria. And how does this grid search work? Let's take a look at that. So first you define the hyperparameter grid. You specify a grid of hyperparameter values for each hyperparameter that you want to tune. For example, if you have three hyperparameter, alpha, beta and gamma, you might define a grid of possible values of, alpha equal to 0.1, 0.5, 1.0, beta is equal to 0.1. So like this, you define all the possible values of each of these parameters. Then what you do is you cross-validate. You split the data set into training and validation sets to perform k-fold cross-validation that we had talked earlier again. And during each fold of cross-validation, you train model using the training data and evaluate its performance using the validation data. So you evaluate and validate. Then for each combination of hyperparameters in the defined grid, you train a model using the training data with the current hyperparameter values and evaluate the model performance using the validation data and record the evaluation metrics, accuracy, F1 score, etc., as applicable. And you repeat this process for all combination of hyperparameters in a grid. Then you select the best possible hyperparameters, best parameters that give you the best results After evaluating all combinations, you select the combination of hyperparameters that yield the best performance according to the chosen evaluation criteria. And this combination represents the optimal hyperparameters for model based on the training and validation data. You can optionally evaluate the test set also with the selected hyperparameters on a separate test set to estimate the performance on the unseen data. This helps ensure that the selected hyperparameter generalize well to the new data as well. So grid search is a straightforward and exhaustive method for hyperparameter tuning, but it can be computationally expensive because you're going to do a lot of combinations, especially when dealing with a large number of hyperparameters, a wide range of possible values of each hyperparameter. Despite its simplicity, grid search is widely used and serves as a baseline for more advanced hyperparameter techniques such as random search and Bayesian optimization. So that's what we thought we would share with you about grid search. Then what is random search? The second technique that we talked about. So random search also is a hyperparameter tuning technique that in a similar way for machine learning models. But unlike grid search, which systematically evaluates all possible combination of hyperparameters within a predefined grid, random search randomly samples hyperparameter values from a specified distributions and evaluates the performance. Now, how does this random search work? Let's take a look at that. So first what you do is you specify probability distribution of each hyperparameter that you want to tune. For example, you might define uniform distribution of continuous hyperparameters and discrete distribution for categorical or category type hyperparameters. Then you cross-validate. Split the dataset into training and validation set to perform k-fold cross-validation. And during each fold of cross-validation, you train the model using the training data and evaluates its performance using the validation data. Then you get into random sampling. You split for a specified number of iteration or until the stopping criteria is met, you sample the hyperparameter values from a predefined distribution for each hyperparameter. This random sampling process generates a random combination of hyperparameters for each iteration, and it's a very useful process. Then you get into training the model using the sampled hyperparameter values in the training data, evaluate the model's performance using the validation data and record the evaluation matrices like accuracy, FN score, etc. Then you repeat the process for the specified number of iterations or till the stopping criteria is met. And after evaluating the sufficient number of iterations, you select the combination of hyperparameter that yielded the best performance according to your chosen evaluation matrix. Now, this combination represents the optimal hyperparameter for the model based on the training and validation set. You can optionally again evaluate on the test set. You can with the selected hyperparameter on a separate test to estimate the performance on unseen data, and this helps ensure that the selected hyperparameter generalizes well to the new data. So random search is a more computationally efficient alternative to grid search, especially when dealing with a large number of hyperparameters, a wide range of possible values of each hyperparameter. By randomly sampling hyperparameter values, random search can explore the hyperparameter space more effectively and converge to good solution faster compared to grid search, particularly when the hyperparameter space is high dimensional or contain complex interaction between hyperparameters. Random search is also widely used in practice and often serves as a baseline for more advanced hyperparameter tuning such as Bayesian optimization. Then let's take a look at the Bayesian optimization. What is Bayesian optimization? Bayesian optimization is a sophisticated method for hyperparameter tuning, especially useful when dealing with expensive to evaluate objective function. Unlike grid search and random search, we explore the hyperparameter space by exhaustively evaluating predefined points or randomly sampling points. Bayesian optimization builds a probabilistic model of the objective function and uses it to select the next set of hyperparameters to evaluate. Now, how does this work? Let's take a look at this. Here, first you do is you define the objective function where y is a function of fx, where fx represent the hyperparameters of the model to be optimized. The objective function evaluates the performance of the model for a given set of hyperparameters. Then you select a probabilistic model, choose a probabilistic model to represent the objective function. Gaussian processes are commonly used as probabilistic model in Bayesian optimization due to their ability to model complex nonlinear relationship and provide uncertainty estimates. Then you select a small number of initial samples of hyperparameters and evaluate the objective function to obtain performance metrics. And these initial samples are used to bootstrap the probabilistic model. Then you iterate in following steps till your stopping criteria is met. You update the probabilistic model based on the observed data. Then you choose an acquisition function known as also a utility function that guides the selection of the next set of hyperparameters to evaluate. Then use an acquisition function to select the next set of parameters that maximizes the expected improvement or acquisition value. Then you evaluate the objective function with selected hyperparameters to obtain the performance metrics. And finally, you incorporate the new data, hyperparameters and performance metric into data set to obtain the to train the probabilistic model. And then you continue to iterate using this optimization process until a predefined stopping criteria is met, such as maximum number of iterations or convergence of the acquisition function. You can also select best hyperparameters by after optimization. You select the best hyperparameters that yielded the best performance according to the objective function. So Bayesian optimization efficiently explores the hyperparameter space by leveraging information from previous evaluations to guide the search towards promising region. By iteratively updating the probabilistic model and selecting hyperparameter that balances exploration and exploitation, Bayesian optimization can quickly converge to high-performing solutions with fewer evaluations compared to random search and grid search. This makes it particularly suitable for optimizing machine learning models with expensive evaluation procedures such as deep neural networks trained on large data sets or models requiring extensive computational resources. The last one is genetic algorithms. So genetic algorithms, GAs, are a type of optimization algorithm inspired by the process of natural selection in genetics. They are used to search for optimal solutions for optimization and search problems by mimicking the principles of biological evolution. Now, how does this algorithm work? Let's take a look at that. You start by initializing a population of candidate solutions, individuals randomly or using some heuristic method. Each individual represents a potential solution to the optimization problem and is typically encoded as a string of parameters, a vector of values. Then you evaluate the types, the fitness of each individual in the population by applying the objective function. The objective function assigns a numerical value or fitness value for each individual, representing how well it solves the optimization problem. Then you select individuals from the current population to serve as the parent for the next generation. Individuals are selected with probability proportional to their fitness, favoring individuals with higher fitness value. You commonly select common selection techniques includes roulette wheel selection, tournament selection, and rank based selections. Then you create offsprings, children, by combining the genetic materials of the selected parents through combination, crossover operation. Crossover generates new individuals by exchanging genetic information like swapping substrings or merging vectors between pairs of parents. Then you get into mutation. You introduce genetic diversity into the population by applying random changes, mutation to the genetic material of the offspring. Then the mutation operations modify genetic genes and parameters with low probability to prevent mature convergence and explore new regions for each search space. Then you create the next generation population by replacing the least fit individuals from the current population with the offspring generated through crossover and mutation. Depending on the replacement strategy, individuals may be replaced randomly based on the fitness or through elitist selection to preserve the best individual. Then you repeat the selection, recombination, mutation and replacement steps for a specified number of generations or till a termination criteria is met. The termination criteria may include reaching a maximum number of iterations, achieving a satisfactory fitness level, or stagnation of the population. And finally, you extract the best individual or individuals solutions from the final population as the output of the genetic algorithm. These individuals represent the optimal or near optimal solutions to the optimization problem. Now, genetic algorithms are particularly effective for solving complex optimization problems with large search spaces, nonlinear objective functions, and multiple local optima. These are widely used in various fields, including optimization, engineering design, scheduling, and machine learning, where traditional optimization techniques may be impractical or ineffective. Despite their computational cost and potential for premature convergence, genetic algorithms offer a powerful approach to finding high quality solutions to a wide range of optimal optimization problems. So what is next after training and evaluating multiple models in model selection and evaluation process? Any thoughts? So the next thing is to compare the performance of different models in architecture to identify the most effective one, right? And that is what we will do in the next lecture. We will talk about how to compare the performance of different models in architectures to identify the most effective one. So thank you so much for watching this 10th algorithm selection and development lecture in this course, Master in Artificial Intelligence. I hope you continue to learn new things, continue to enjoy, and I do look forward to see you again in the next lecture. Please feel free to message me if you have any questions. I'll be happy to answer a question and also download the PDF file anywhere that you need to.